Hello, our project is game theory based scheduling and load balancing for the cloud. This we are implementing on a real time basis by setting up a private cloud and then with respect to a public cloud of SkyDrive and Facebook. Now you could have a look at this. I am running a local host service as port number 8090 with main image service.asmx. This is main component as RGB to gray, which converts an image into grayscale. CPU counter gets the CPU usage of the server. Performance will give the memory performance of the server. The same service is running in one of the real sites, Grasshopper network, where you can see the same web services are running. The work is developed in .NET 2012. Coming back, this is the solution explorer. Come to app.config. Now as we will be transferring a lot of images, we want a lot of buffer. Generally the buffer range is set as 65,000. So just increase the maximum receipt size such that it can handle a lot of images. This is the first thing. Now coming back to our form, if we execute, it is organized in this way. When we browse a directory, we are basically giving input as jobs. These jobs are to be scheduled and balanced over the cloud in order to minimize the cost for the user as well as the load in the server. So it is both user centric as well as server centric. The partitioning based load balancing is a technique which is predominantly a game theoretic technique. We are going to first divide the loads into clusters, classify the clusters, and then followed by checking out the cost of the server based on bandwidth parameter, latency, load, etc. And based on the cost, we are going to schedule. Now, if I could show you how the things works, I'll be selecting a test directory, say a test directory. We have four options. Update, which will be keep on checking the server cost before every scheduling and balancing. Don't update, where the server cost would be taken only once before the polling of the jobs. All of these images will be now considered as jobs. There are totally 5 images out here. And there are two scheduling methods, phase scheduling and FCFS. FCFS of course will be sending one set of images to one server, the other set of images to other server in the serial execution, whereas the fair scheduling technique is going to try to balance the load fairly. Now we have this many images. As you can see, I have kept 2 images as larger side. If we can click for partitioning, if we look at the cluster for 5 images, you can see the last 2 images which are bigger have been classified as one group, and rest of the nodes have been classified as one group. What my code does here is it checks the cluster heads, and based on the cost of the cluster head, it groups them, followed by extracting the cost from the labels from server performance, and then further carry out the scheduling. So if we continue, now it is going to wait for server performance. As you know that we are running a method at the server by means of which the application can poll the performance of the server. Here we go. The load 1, server 1's cost is high, server 2's cost is low, server 2 is the local server. It's a scheduling based technique. If at all a job at the time of scheduling hadn't been successful, it would have been sent to another server. This is the second category job coming to second server, and so on. And you can keep on checking the load getting changed in every execution. So the jobs will be distributed. This lower half is for server 1, the upper half is server 2, and you can see this is a non-blocking method, that is jobs are being scheduled even before we get the result of the earlier job based on the calculation of the cost. So here we are trying to use game theoretic approach, and you can see the total time is 74 seconds. Now here we try to use the game theoretic approach for scheduling. Here I'll again be using the same job, but now I'll be using don't update method such that you can see server performance should not be varying before every job is being scheduled. So it's going to calculate the server job once for the entire job pool, and then this is the cost. Local, as you can see, is less, and because there is no update, it can quickly complete. So this is how it works without update. Now we are going back to the same technique. Here we'll be utilizing FCFS technique. So as you can see, we had used fair scheduling with update and don't update. Now we'll be using FCFS with update and don't update. So in FCFS, the order of execution remains same. As you can know, that updating based technique is time consuming because it has to poll the server performance before every schedule. As you can see, the remote server apparently at this stage at lower cost, so the files have been sent to remote server. And long after scheduling the process, the job should come back and will be stored over here. Once all the jobs will be back to the broker is going to display the total time that had taken for the jobs to arrive. Now we'll again perform an experiment for FCFS with don't update. Due to high memory consumption, we need to close down the simulation and start it once more. So we'll use don't update with FCFS, and we'll be using the same performance can be taken for scheduling with load balancing, all 8 options. So I'll be using update, fair scheduling for scheduling with load balancing. Now the concept of scheduling with load balancing is instead of game theoretic approach of clustering, here we'll be checking out the cost of the server, and whichever is lower cost, larger image will be sent to that lower cost server. Whichever is the higher cost, lower memory images will be sent to that server, so that load is balanced and time requirement is minimum. However, this technique with update method will take more time to get executed because it is not using any artificial intelligence in order to determine what could be the next job is up to. So more or less scheduling with load balancing is also a blocking technique where you can see that it will be waiting for a specific job to arrive before it sends another job. So and for every update method you can observe the server performance getting update before every scheduling. We have basically taken two servers over here. Instead of that, you can also carry out the simulation on a pole observer, group observer, where the images will be transmitted to different servers. Every time we get a result, the result will be basically stored in database, and you can view the performance graph. However, I do not have sufficient number of points over here, so I'm going to show you the result with respect to test data that I already have. So I'm using an existing performance data set. We can go with the performance, and you can see all the 8 methods comparison would be shown over here, the way jobs will be scheduled. Now one thing that you'd be able to know is, yes, with respect to number of jobs, the average time for scheduling does increases. At the same time does increases, but if you look at this graph, which is the CPU utilization factor, you'd see one strange thing is CPU utilization does not increase exponentially. Of course, for a couple of methods it's higher, but generally CPU utilization factor will be kept at average. So even though the scheduling time increases, which is understandable because of the amount of load, the load in the server due to load balancing policy is been maintained consistent. And if you look at the bandwidth utilization, this is also an interesting graph which gives the bandwidth utilization within the servers, and you can see that's pretty consistent over change of images. So we can say that because of load balancing factor, the bandwidth utilization is also almost consistent. And this technique, once tested with both conventional load balancing as well as game theoretic approach of load balancing, does also do a real-time testing of publishing a group of image over the real-time web. So in order to do that, what we do is we basically take the same test folder and we use two public cloud. One is SkyDrive. We use this for storing the images. Now our test is to see the theory that we have developed, how far it is applicable for real-time application to push the data to the cloud. So because we cannot deploy our own services, the service that we are using pertaining to this to cloud is nothing but the storage service. Once we have logged into SkyDrive, we'll minimize this option, and we'll also log into Facebook. These are the two public clouds. So once both these techniques have been done, we can see the amount of time it takes for the data to be covered. We can create real-time process with load balancing, and if I can show you the data here, so the images gets published to both Facebook as well as SkyDrive. It gives me the final time that it had taken for this to send the images. Now for testing, I'll just open my Facebook account in order to show you what's up with it. Now as you can see that we are testing the folders, and therefore these two images had come to Facebook. At the same time, let me open my SkyDrive account to just check out how many images have gone to SkyDrive. Total time that has been taken for both this technique is 44 seconds to upload this many images. I'd rather delete it. So you can see this image which was here, these two images has come to my SkyDrive, this image and this image over here has come to SkyDrive. So this is how basically the overall thing is performed. So we can not only develop an algorithm for scheduling and load balancing, at the same time we can run it online, and based on the performance I'm going to show you how the execution changes. Let me browse the directory here. Let me say partitioning based balancing. Keep observing the cost component. You can see server 2's load is low, so we are expecting the larger image. This is the larger image with 10 MB size coming down to this. Now as it is getting processed, this is getting changed, server 2 is becoming overloaded. We can also test the CPU performance. Of the local server, just similar to this one. So you can see the memory usage of the server, and you can see the memory usage of the server over here. You can see the load usage, the amount of CPU that is being required, and also communication latency. So as you can see, this is almost the same value that we'll be getting, and every time that we carry out this test, the places where the images goes or the server where they are scheduled will get changed. So right now I'm making the same test once more with update. This is a typical case. As you can see, this image has gone to server 2 remote host. The second image also goes to server 2 remote host even before the result of the first images arrived. Now, second image was belonging to second category of images, but by the time second image was supposed to be scheduled, the load composition of both server 1 and server 2 had varied. Therefore, instead of going to server 1, the second image had also gone to server 2. Now, by the meantime, the load component of server 2 is been reduced significantly, so you can expect the other images to come to server 1. As you can see, the other images are now coming down to server 1, and because of non-blocking technique, the result of one scheduling process will be done before the result comes. So this is how the simulation works. And after every operation, you can actually check out over here. These are the main techniques. CPU, I'm using 5 load, so you can see a new mark over here. I'm using fair scheduling with update, so you can see the orange color mark here. It shows all the CPU components over here, and I had used for 5 images, so you can see for web also a 5 image bar is there. It had taken 44 seconds. As you can see, the 44-second mark will be there. So this is how basically entire thing works. Every time you run, the overall job allocation will keep on varying based on the preferences you have given. If you have given don't update method, once the composition is being made, it doesn't get changed overall. Now this has got also a very interesting theory of job reallocation. Now consider that you do not get the result over certain period of time. Under that situation, it's going to get transmitted also to another server. As you can see, this image has been sent to both the server. Now this is a typical scheduling and load balancing theory. When you don't get the result for a particular period of time, server understands that the result has not been obtained and it reschedules the job. So this is a fantastic theory of this work of rescheduling. So once you have a server not responding in proper period of time, you also send it across to another server so that you get the job done in early. Hope you've enjoyed the demo of this real-time load balancing and scheduling for cloud, especially using Game Theoretic approach. Thank you.